Okay, so as I said, now the new people have joined us. The title, as I said, is Future Aspects in Computational Mechanics. I did not put the slides. I will put only the video for you who are interested in this topic. It's a very important topic. There are a lot of research groups which are now working on such topics. It would be maybe like a topic for the master thesis. Or maybe PhD thesis. So you will see a lot of announcement in this regard. So the future aspects include machine learning-based multi-scale material modeling. And as I said, maybe you would like to build a continuum mechanical model. So based on the issues that we have also learned in this course, we want to build this model to solve this boundary value problem, which is maybe a very simple boundary value problem. Let's take a one-dimensional structure. It's fixed from the bottom, and you pull this from the top by a certain force. So it's force controlled, and you would like to compute the displacement. What we do is first we have the universal laws, so they are independent of the material behavior. Whatever material you have and you want to treat on a continuum level, first you define the kinematics, which is a relationship between the strain and the gradient of displacement. So if you assume that you have only small deformations, then you can go for this linearized strain tensor. If you have large deformations, so we figure out that you have a large deformation, then you have to add some additional terms here. We have already learned the difference between small and large deformation, but this kinematics will not change whatever your material is, elastic, inelastic, and whatever. The same is applied for the balance equation. It's also a universal law. Whenever you have a material which is, or a structure which is in a balanced state, then you can apply the balance equations. You can add or maybe remove some terms here. For instance, if we say that we have a quasi-static, so we apply a slow load here. So maybe you can neglect the inertia term. Otherwise, you can take this quasi-static formulation. And also for the boundary conditions, it's the same. So we have this definition. The stress multiplied by the norm on the boundary, it will give us the traction vector at the boundary. Or if you have displacement control, in this case, we are fixing the boundary from the bottom, so you can predefine the displacement at the boundary, and then you have these boundary conditions. So what I presented here is our universal laws. They are independent of which kind of material you are treating, and then we collect this information in what we call constraints. Now we would like to understand what kind of material behavior we have. What we do is we look at the behavior of this structure in laboratory. As I said, here you can go for a uniaxial test, and you look how the behavior is. It linear relationship between the stress and the strain? Is it nonlinear? Do you have remaining strains if you remove the load? So this is one way. The other way, if you understand the composition of your material, then you can go for lower scale simulations. Like in case of molecular dynamics, you know the molecules, what kind of material you have, then you can apply alternative or surrogate model on the computer. If you are studying, for instance, the flow in a Porous material, then you can go for lower scale simulations like the Lutz-Boltzmann. So I will go for this later. So what's important here, this experiment will give us data points, which you can also plot on this sigma epsilon curve. And then we would like to know what kind of material behavior we have afterwards. So this is an empirical step, which is a material law. It gives us a relationship between the stress and the strain. And this is the question mark. So what kind of material behavior we have here? We have a data point, and then we have the constraint. If we choose some kind of material behavior, maybe you have learned this from other courses, then this material law or constitutive model should fulfill certain constraints, like objectivity. It should be independent of the observer. And maybe if you have dissipation, or in general, you should fulfill the entropy inequality or the restrictions of thermodynamics. This is also an important issue, especially if you have plasticity. So you should make sure that the dissipation is always positive. So the phenomenological material model, as I said, we have the data point. You can, if you load and unload, maybe you can go back to the initial state. Then in this case, you will have elasticity, but you see it's not linear, so we have nonlinear elasticity. If you say that, okay, or if you observe that you have remaining strains, it means you have maybe some kind of plasticity. In this case, you will use, for instance, elastoviscoplasticity or something like this. So it's some kind of empirical. It's a line equation. And then what is the solution in this case? So we have the constitutive model, and then you have the restrictions. Then the intersection between these curves would be our solution. So these are the possible solution. Usually, this sigma epsilon relationship, you include this in the balance equation. So if you go back here, so you put here divergent, then sigma. Sigma is our constitutive model. And then by applying the weak formulation, we would have also a possibility to give the boundary constraints. And the kinematic is also included in the strain here. So you have all the information in this governing balance equation, and then you solve this problem. And the solution will be these points. Now, some new groups or some research group, it's not really new, but now it's getting more attention. They start by applying what's called data-driven computing. And the idea here is not is to avoid proposing this phenomenological material model, is to go directly from the data point to the solution. And the idea here is to define this optimization problem. So find the solution, which would be the stress strain, which belongs to the data point, which you have obtained from like experiments or from lower scale simulation. So find this solution, which is the closest to the exact solution, which are the sigma epsilon, which is found on the constraint. So this is the solution which is fulfilling the constraint, so in universal law. And this is the data which we have. So it's a minimization problem. So that it's a distance between S, the data which we have, and the optimal solution, and so S star. It's a standard optimization problem, so you can go for Lagrange multiplier methods, where you multiply the constraints, which are our C, so our universal law, the balance, and the kinematics. We will multiply them by Lagrangian multiplier, and we formulate our optimization problem. So you take the derivations with respect to the corresponding variables, and then you have like several equations to solve, and then you will get the solution. It's a standard optimization problem. There are a lot of ongoing research work on this issue because you'll have a lot of challenges if you have elastic behavior, inelastic, and multidimensional computation, and so on. So you'll have a lot of issues. So this is one possibility, but in my group, we don't really apply this. We apply alternative way, which is machine learning regression technique. We use in this case like artificial neural networks, and we apply here this we call this machine learning constitutive relationship, which give us or where we have, for instance, the strain as input, and then we have the stress as an output. This is a possibility. You can have it other way around. You could have the stress as input and the strain as output. This is also possible, and we use the artificial neural network. As I said, if you have any question, interrupt me. Otherwise, if you write the question in the comment, then we'll go back to this at the end of the presentation. Okay, so let's go for the first like example. I show you this one of the examples that we are really also we have published. So we assume that we would like to go to model like a composite material, and this composite material on the lower scale, it consists of like a kind of matrix, and we have inclusions, so it has like two materials. We take like a small sample, which is a representative volume element, or if you would like. So if we zoom in, we would see here the inclusion, and we have the matrix. So take one of these units as a representative volume element, and we'd like to know what kind of behavior we have here. So we could apply here as a surrogate model, a kind of finite element model, where both the inclusion and the matrix will be like discretized using some finite element method. We can propose on this scale also some kind of maybe inelastic material behavior. In this case, it was a plasticity model. And we use this lower scale simulation. So we take this representative volume element, we apply loading in different directions. We have tension, we have shear, we have tension in two directions, and we can rotate also the representative volume element and so on. So we generate a database, and machine learning needs really big database to give you a good model. This is the first step. So we go for lower scale, we choose a representative volume element, and we apply loadings to generate database. Once we have this data, then we can take this and use this to generate machine learning material model, which is simply give you the relationship between the stress and the strain, and which can include also additional information like the anisotropy, and also maybe it could be inelastic response. So this is a material model, and if you are applying finite element on a big scale, then you can go for you include this model instead of the phenomenological material model, and then we can solve a boundary value problem. This is one way, or this is one example. The second example, we apply this idea also to model crystal plasticity. So assume that we have, for instance, this is a crystalline rock, but you have a lot of materials which have some crystalline microstructure. And this is in crystal plasticity, so the important issue, as the name says, it's a plasticity. And this depends on the type of the crystals which you have. So if you have this FCC, this single crystal, and we have in this case like several slip surfaces. In this case, it's I think 12 different slip systems. So you can take one crystal or a polycrystal, so several crystals, as a representative volume element. In this case, you can go for to generate a database from different loading conditions in different directions. You can rotate the crystals and so on. And then you generate a machine learning material model then based on this database. And then again, as we did before, you include this in the finite element framework, and you will at the end solve big boundary value problem without the need to figure out like the material parameters. So they are already included in the machine learning model. But as I said, the key point here is to generate the database. The alternative the third example would be, for instance, Porous media mechanics. Again, we choose a representative volume element. In this case, it's could be saturated porous media. Would be then they have grains and we have some water in it. So this would be the starting point for our representative volume element, which we need to generate the database. And this, from the lower scale, we build like representative volume for the representative volume element. We can apply, for instance, the Lutz-Boltzmann method to simulate the flow in this representative volume element, or we can apply the discrete element methods to simulate the deformation. Once we have generated the database, then we can go for machine learning material model. This could include like the relationship between the stress and the strain. As I said, in this case, we don't really care if it is elastic or inelastic. So it's simply a relationship between the stress and the strain. This, of course, will affect what kind of machine learning model we would apply, but the material parameters would be like implicitly included here. We could have other like constitutive models like the retention behavior or the permeability. Then we apply this in the finite element framework. In this case, you can solve big boundary value problem. So these are like the three examples which will I try to present to like give you an idea in which place we will put the machine learning material model. However, there are a lot of other applications and a lot of methods to include machine learning models in within computational mechanics and within finite element method. For instance, you will see people going directly from the from the boundary value problem to solve so from the equations to the solution. Some people use finite or smart finite elements, so they replace the shape functions by some kind of machine learning models and so on. So you will have a lot of different applications, but what I'm doing here in my research group is this application. Now, just to give you like a big overview, machine learning, you have a lot of different ways for learning. There are three major categories, which are the reinforcement learning, the supervised learning, and we have unsupervised learning. For the reinforcement learning, we have mainly the control. In this case, this is mainly applied within robotics, but we can also apply this within within the computational mechanics. I apply this for figuring out the the neural network settings, so what we call also the meta parameters. This is also something very interesting here, and I will talk very briefly about this. Most of the time for the constitutive modeling, we use the supervised learning, and namely the regression, because we would like to predict some values. In this case, we have supervised learning because we know the real stress and the strains from our database, so we know already the exact solution, and we train our neural network to figure out the corresponding weight and biases. In this case, I'm applying here feed-forward neural network and a recurrent neural network. This depends, of course, on what kind of material response we have. So the aim in this research work first is to apply an accurate and computationally efficient multiscale approach. This represents an offline multiscale because we generate the database in different steps, and then we use this to train our model, and then separately. So, and then in following step, without like applying the macroscopic before, when we have already the trained model, then we can go for a continuum model. So in a separate way. So it's offline. And the steps, as I said, they are first we generate data sets like from lower scale simulations. If you have experiment, would be great. If you don't have experiment, then we go for lower scale simulation. We train the data sets based on, as I said, the machine learning. And then when we have the trained model, then we integrate this within a finite element environment. The advantage here, we would like to overcome the first the disadvantage of computationally expensive online multiscale homogenization methods. So in these online methods, you will solve at each Gauss point a representative volume element, and then you have to, at each time step also, you have to resolve this RVE again and so on. So it's very much computationally expensive. And we would like to overcome the inaccuracy in connection with phenomenological models, because here we go directly from the data to the model. In this case, we don't need to explicitly determine the material parameters. So this is what is implicitly included in the machine learning model. And it allows us also to include whatever information you have. So you can include a lot of microscopic information. I will come back to this later. Which might be also like not considered in the phenomenological model. So this is also something which is, it allows you maybe to discover new dependencies which you did not notice before. And however, there is the advantage here, or the need, let's say, you need a database, so which should be like big database. Otherwise, if your data is very inaccurate or very small database, so most probably you will not get an accurate model. Okay, so after this short motivation and explaining the aim and the method, we will talk a little bit about the basic ingredients of artificial neural network. Those of you who attended, for instance, the machine learning course in our institute or in other institutes, they will be familiar with these fundamentals. I assume some of you did not attend this, so I will just review this. And so, by definition, a neural network consists of connected neurons or cell structures in layers. We have, as usual, we have the input layer. So it would be in our case, if we go for the stress-strain relationship, the input would be, for instance, our strain components. The output would be the stress in this case. And then between them, we have the hidden layers. They successively process the input signals, and they have a certain structure, and then they have also certain properties which have to be specified. The size of the input and output layer is predefined by the size of the input and output vectors. So if we have strain, let's say in two-dimensional configurations, then we would have three independent strains. If we have isotropic strain tensor, would be the epsilon 11, epsilon 22, and epsilon 12. So it would be like 3. And then the same for the stress. However, the hidden layers, their numbers and the number of neurons per layers, they have to be specified by the user or by the programmer. I mean, if you change them, then you will also change the performance of your neural network model. That's why you have to be careful about this choice. In my case, we could also specify this using the reinforcement learning, and this is what would also be discussed. So let me call this the number of hidden layers. So this is the like the abbreviation, and the number of neuron layers. It's also an abbreviation for the second parameter. So these are two meta or hyperparameters for our neural network. Then we have also what we call the activation function. So let's take, for instance, the feed-forward neural network. So the output signal here of a certain neuron, which we call, we'll give him this like index k. So in a fully connected layer, so this layer here is fully connected with this neuron. So we'd have several inputs to this neuron here, where we have these signals like x1, x2, and xn. So this output signal can be computed by this function f. And this is a simple polynomial function. So, but it's not like it's not one equation. It has some kind of matrix representation. So, which includes this wki, which is a matrix of weights, and bi or bk in this case, it will be a vector of biases. These weights and biases is something what we would like to figure out in the training. So this is the whole training process, is to find the optimal weights and biases. Just like when you have an equation for the line and you would like to know the inclination of the line, and then you search for the right parameter like a multiplied by x plus b. So you have to find a and b. This is the weights and the biases. And f would be then what we call the activation function. It's also, there are several activation functions which we will find in the machine learning softwares. They are selected by the user, and they define the output of the node. In the literature, you will see, for instance, what we call sigmoid. It has this equation. It gives you an output between 0 and 1. And then we have the hyperbolic tangent. It gives you an output between -1 and 1, and we have also the rectified linear unit. The output would be between 0 and infinity. So depending on the data which you have on the aim of the training, you can also choose your activation function. Most of the time I use this sigmoid function, which seems to be good for our machine learning material model. But this is also a hyperparameter which we have to figure out, and that's why I wrote this with red. So we'll go back to this in the connection with reinforcement learning. Then we have the supervised training of the neural network. If we take the feed-forward neural network as an example, so the problem would be like find the right weights and biases so that the objective function is minimized. So the objective or loss function is simply the difference between the true output and the predicted output, which you compute here from the based on the activation function, but for the last layer. So this is the output, which is connected to the output layer. And if the difference between the true and the predicted values is very low, it means that you have already found the correct or the proper weights and biases, and your solution is more or less optimal or almost optimal. So you will never get in the training zero like objective function, because in this case it will be exact, which is it's not realistic. So you'll get very low objective function, which will where you could also like in finite element you put like the tolerance. In this case, you will put like 10 to the power of -6 or 7 as a number which mark the convergence of your in the training. The search for the proper weights and biases, it's a kind of also optimization problem. So assume that you have a certain function and we would like to find the minimization here. You take simply the derivation and the or the gradient, and then you follow, for instance, the gradient descent algorithm. So the gradient should decrease until if you have like the total minimum, in this case you will have almost 0. And this figure here illustrates how you, by iterative way, you find the minimum in your training. You should, however, be careful, because in the machine learning, you could fall in some kind of what we call local minimum. So you train still your the objective or the loss function is still big, but you are iterating more and more, but you are not getting better accuracy. In this case, you are maybe falling in this kind of what you call local minimum. In this case, there are some techniques to try to push the solution, maybe to go for some kind of global minimum, which is better. There are some techniques like drop out layer, so you neglect some of the layers, and cross validation and other techniques, and maybe improve your database and so on. So there are several techniques to avoid falling in local minimum and going for a global minimum. Also, what kind of optimizer you follow? So I mentioned the gradient descent algorithms. There are several optimizers like CGD. This is the also widely used. You have Adam. You have they have different abbreviations. So I am not mentioning here exactly what these abbreviations refer to, but these are several optimization schemes which you will find also in machine learning algorithms. There are additional schemes which are not mentioned here. So the idea here, you have to choose the optimizer, and this is also a kind of meta parameter which you have also to specify as a user. We could also use the reinforcement learning to find the best optimizer. And then you have to choose the structure of your neural network. So we have to find the proper selection of the type of neurons. For instance, the feed-forward neural network, it passes the data in one direction, so from the input to the output to the output in one direction, and this is can be applied for what we call a path-independent response, like elasticity. So for elasticity, if you give certain strain, then you'll get certain stress. It doesn't matter if your material was loaded, unloaded several times. It's a direct response. So it's in this case we would like to we could use feed-forward neural network. But if you have like different behaviors like plasticity, it makes a difference if you have loaded and then unloaded. So by unloading, you will be found on different path. By reloading again, you will get you will follow this new path, not the old path in this case. So it is path dependent. So there are a lot of material responses which are path dependent. In this case, you can use what we call a recurrent neural network, which can process sequences of data, including the output of the previous state, and include this as an input. One of the recurrent neural network methods is a LSTM, so it's a long short-term memory. It's widely used. You have also the gated recurrent unit. It's also widely used. So this is for the path-dependent behavior. Another example, maybe from real life for path-dependent behavior, it's in the weather forecast. So if they want to predict if tomorrow is going to rain or to have sun, for instance, in Aachen, they observe, for instance, that if it was raining 3 days in sequence, then the 4th days we would have sun. But it's difficult to predict if today is raining, if tomorrow will be sun. It's difficult. So, but it's usually rains 3 days continuously and stop after in the 4th day. So the possibility that we have sun, it's much higher. And this prediction would be more accurate than if you say, okay, if today is raining, then tomorrow will be sun. So you'll have a lot of uncertainty in this case. So you can consider several previous historical events if you want to predict the next event. And the same here for plasticity. If you know different data points, then you know that you are, for instance, if you have sigma 1, if your state is sigma 1, then for the same sigma 1, you have different strains. But if you choose several historical events, then you can predict the future one in accurate way. And this is a path-dependent way. And I will go back to this also in different in other example. So these are the basic ingredients of the artificial neural network. You will find in the internet a lot of explanation of this, and this is very helpful. And I hope that you also got the basic idea from my explanation. Let's go for the first example, which is the machine learning anisotropic crystal plasticity. So first, as the title said, it's anisotropic material behavior, and so the material in this case I consider here both isotropic and anisotropic, and by anisotropic it means the material it has some preferred direction. So it's in certain direction the material is stiffer than the other directions. In this case, also the material response or the material model which we will generate by machine learning, it should fulfill the objectivity condition or should be frame invariant. It means if the so within continuum mechanics, if you apply rigid body rotation to the deformed configuration, so if you just rotate the structure that you have, you should not have you should not get different material response. It's just like you deform the material and you change the position of the observer. So if you look at the deformed material from different positions, you should always get the same description of deformation. So this should be observer independent, and this is what's a very important property which should be captured by a material model. And for machine learning model, it's exactly the same. We should fulfill the objectivity. In this case, to do this, we can, as we do also with conventional material model, we could represent the data in spectral form. So instead of taking the stress and the strain component, we go for the eigenvalues and the eigenvectors. Yeah, and then we could also apply hierarchical relations among the physical quantities and the state variables in what we call informed or directed graphs. I will test three variations of this informed or directed graphs. So how we transfer the information between the stress and the strain, and maybe include additional information. We would see that for the same amount of data, so for the same database, how we represent the information. So this numerical test shows that for the same amount of information and data, so the quality of the machine learning model is sensitive to the way tensors are represented and measured. So if we take the component, we'll get different performance as if we take the eigenvalues and eigenvectors, or if we take as we'll see later, the like Euler angles, or we put the data in what we call Lie algebra. We'll see later. So for the representation of elastoplasticity in directed graph, take for instance as a direct relation, we could have the strain and the strain history. So you see we have epsilon n plus 1, epsilon n minus 1 as the input, and we apply recurrent neural network to predict the stress. So this is one way to build our machine learning material model. Second way is to what we could have also the informed or directed graph. In this case, we use the strain as input, and additionally we use the stress history. So let's say for the weather, we predict the weather for tomorrow, and then tomorrow we take the state of the weather, which is already tomorrow, which we already know. We use this as a new input together with the history, and then to predict the weather the day after tomorrow. In this case, for the material model, because we have incremental computation, so at each time step we would have a new unknowns. In this case, we take this stress from the which we have computed from the previous iteration, and we use it as a new input for the following step. So this is what we call informed directed relationship. And then we could have also more complicated graph, which is elastoplasticity graph. So we use the information which we have computed during the generation of the database in the prediction of the output. So in the data generation, for instance, if we use the return mapping algorithm for the plasticity, in this case we have computed like the plastic strain from the previous time steps. We have also the trail stresses. We have like the elastic trail strain and so on. So we have all this data, and we can use them for the what we call directed graph too, which is more complicated. We use here a combination of feed-forward neural network and recurrent neural network, because we have elastic steps and we have plastic steps. So this would be also another option. So we can go complicated or we can go simpler. In the paper which we have published in this connection, we figured out really that this is it was the easiest option to implement and give us very good performance. So let's say the informed direct relation. So it means that it's not necessary to go for a very complicated model if you want to get like a good performance. Maybe a simple configuration would also give you a good performance. So it's for anisotropic crystal plasticity. First, we would like to generate a database. So the material which we have is the face-centered cubic. It has 12 slip systems. And we applied, because it's elastoplasticity, we applied the isotropic, transversally isotropic elastic material response just to enhance or to show that the rotations of the principal stresses, which it has some effect. So in order to test also the performance of our model for objectivity capturing. This figure illustrates the different slip systems. And we apply the ultimate algorithm, which is published in the literature to generate or to solve the one crystal behavior. As I said, we take one crystal as a representative element. We apply loading in different directions. We could also rotate the crystal and apply the loadings again. Here also for simplicity, we applied everything in plane, so we don't have the 3-dimensional, we have only 2-dimensional. And we applied really big database. We had 1,176 different experiments, 24 different loading applied, and we had like 49 different configurations, so rotations. It's not complicated here because everything is automated. So we don't like at each test we run this again. So we put an algorithm where we change the angles, we change the loadings, and then everything will be automated. So the whole database is generated in half an hour. So, but you need to apply the algorithm or to program this correctly. And once we have the database, then we have the second step, which is, as I said, optional. This is to change how the data is formulated. You could apply like spectral decomposition to extract the principal components and the related eigenvectors. So instead of taking the strains in like in their initial shape, we take the eigenvalues and eigenvectors, so in spectral form. And then we have to specify the training, the validation, and the testing database. You can divide this in different ways, but most people do take this. The big part would be for the training, which are used for adjusting the weights and the biases. The validation database, which is independent, it tries to evaluate the accuracy during the training. Some people don't apply this validation data set. They use cross-validation in this case. But it's very important to have testing data set. So it's data which is unseen. You don't include this in any part of the training. And then once you train your model, then you can take this testing data set and see how good your trained model is. So you can calibrate your model or the performance of your model based on this unseen data set. But after dividing, then we have to start with the training. So in this case, we scale or normalize this each sequence of input and output data. So if we are using this sigmoid, and we have seen that the output data was in the range between 0 and 1. You could have data which changing in different ranges. So it's very advantage to have this scaling. Maybe you have, for instance, some components which are changing between 0 and 1 million. And maybe you will include in the training some parameters which are changing between 0 and 0.01. So if you don't scale this to the range between 0 and 1, then one of the parameters which are changing between 0 and 1 million, it will be dominating. So that the small values will not be considered in the training. That's why we scale everything before, and then we scale this back after the training so that you will get the correct prediction. Before the training, then you have to select the settings of your neural network. So the neural network hyperparameters, which are in our case the number of hidden layers, what kind of optimizer we are applying, number of neurons. We have other settings that the dropout rate, activation, neuron type. So if we have feed forward or recurrent neural network. We go, as I said, for supervised machine learning, and if we want to, for crystal plasticity, it's plasticity, as I said, so it's path dependent. So we take this STM, which is a recurrent neural network, and I use the software Keras, which has a TensorFlow in back as a machine learning package, so as a backend. Keras is developed by Google and it's open access. You can simply download this, and it's very easy to handle. Then we have the to specify our objective or loss function, and we use this to enforce the objectivity of our material model. So in this case, like this is for illustration, we could have the strain component. So if it's a 3-dimensional case, then we have this 6 here, 6 component for the strain, 6 component for the stress, and then we have here the hidden layers and so on. And then in the training, the aim is to minimize the discrepancy between the predicted and the true data. So the true data which we have from our data set, and then the predicted, which is based on the chosen biases and weights. And as I said, we have to find the minimum of this. The objectivity can be enforced through treating the loss functions in spectral form. So instead of taking the component or the real component of the stress and the strain, we could take the eigenvalues of this. In this case, also we can also figure out the rotation tensors simply based on the eigenvectors. So we can construct the rotation tensor of the strain and the stress. In this case, to make sure that the predicted and the true stresses have the same orientation or the same eigenvalues, then we can construct our our loss function based on the rotation. So we can specify the rotation matrices, which is the distance between the true and the predicted rotations, so that the problem will be can be specified as this one. So we have the true rotations and we have predicted rotations, and the aim here is to minimize the distance between the true and the predicted rotations. Those of you who attended robotics courses, they should be familiar with these rotations because it's a very important topic there. And as I said, we would have then modified loss function, which includes now enforcement of objectivity. So minimize now the loss function, which now includes a part which is related to the principal variables or the eigenvalues, and a part which is related to the rotation. Okay, so this is the modified loss function, which is connected with the enforcement of objectivity or like frame indifference. And now just going through some other details. So instead of taking rotations, we could take the angles. So the Euclidean distance between the Euler angles would be, in this case, an option. So this is a specification of the exactly of this term here. This is an option. However, we would have, if we take the Euler angles, we would have a problem with what we call non-uniqueness. It means you could have a vector which is referring to a certain direction, but the Euler angles could be different. So we could have B, B, and 0, and 0, B, 0. It's exactly the same vector and the same direction. That's why we would have non-uniqueness in the solution. And this is a problem if you are applying the machine learning. In this case, you will have different or exactly contradictive predictions. Then we have thought about something different, which is geodesic on the unit sphere. So you make a mapping from the from Lie group or this Cartesian space to the what we call tangential space. So Lie algebra. In this case, we don't use the Euler angles, but we use the what we call the skew-symmetric counterparts of this rotation matrix. So we'd have this, then we would have this also as a matrix, W. It has also 3 components, so it's not really more expensive as the training. It's exactly the same cost. And then we can now apply what we call the distance function of the loss function on the Lie algebra. So it's given in this form. So I don't want to go in more details here. I know it's not easy to understand from the first sight. But if you are interested, we have a nice paper to this topic. We explain this in details. I will refer to the details of this paper at the end of the presentation. Now we have trained the model and we train different graphs. We can now compare between the different schemes and the performance of this. So we specify what we call the empirical cumulative distribution function for the scaled MCE, so the the errors, let's say, we see that different schemes will give us different behaviors, and this is a different testing case. So if we have different tests, then if this curve is straight and vertical, it means we have almost the same order of error in most of the tests, which is a very good issue here. So we see here we have also a straight line, which is almost like for the same for all tests. It means our model is consistent for all predictions. So it's not like sometimes give us good accuracy and sometimes give us like bad accuracy. So it has almost the same order of error in most testing of the cases. And this is a good issue. And then you see here we have the errors 10 minus 3 and 10 minus 3, 10 minus 4. So we have seen here that for this, if we use this Lie algebra for the rotation, and we use this, and we look at the principal variables, then we have very good predictions. The rotation prediction is less accurate, so we see here, but we still, if we use this directed graph one, which we have only included the output from the stress, then we have very good accuracy also, and this is which shows that our model was giving very good accuracy in this case. We compared here between we have here the stress strain behaviors for the normal for the here epsilon 1 2 and the stress corresponding stress for the true data and the predicted data, and we see even if we have like complicated behavior, our machine learning model is predicting to a good accuracy the behavior here. Okay, we have another example which is from the Porous media mechanics. In this case, we go exactly to the same idea. We choose first a representative volume element and consider this as unsaturated Porous media. So we'd have here like kind of solid phase, we'd have fluid phase and like a liquid, and then we have a gas phase. We apply homogenization here. And in this case, so we'd have gas, liquid, and the solid in the homogenized model. I think those of you who are attending Porous media mechanics course, they understand this very well. Then in unsaturated Porous media, then we have the degree of saturation as an important parameter. And so I don't want to go in details here. What's very important in unsaturated Porous media is to find a relationship between capillary pressure and the degree of suction. And this is a constitutive model, which is most of the time it's phenomenological model. One of the important material models in this case is the Frank-Newton model. It's simply a curve which does not really distinguish between the like drying and wetting curves. So it includes a lot of errors from this perspective. And then you have a lot of parameters which you have to figure out. It's more or less fitting parameters. So it has a lot of possible errors in this case. So we would like to avoid this by including machine learning. We have also another constitutive model, which I'm not addressing here. So simply the relationship between the total stress and the effective stress. And then we have the pressure here, net pressure, which includes gas and liquid pressure. So this is a second constitutive model, but the focus was actually on this one in this research work, which we have applied. First, we need to generate a database. As I said, we have different constitutive models, so we could have different lower scale simulations, like applying the discrete element method to figure out the relationship between the stress, the strain and the stress. We could apply like a Bohr network model to generate the behavior or the relationship between the saturation degree and the capillary pressure. So to figure out the retention behavior. And you see here we have capillary pressure. We could have also porosity as a microscopic information, which is also included in the model. We could apply also Lutz-Boltzmann methods actually to figure out the retention curve, or also to figure out the permeability, which also represents some kind of constitutive model. So the relationship between the pressure gradient and the fluid velocity. So from here we are generating actually the database, and then we go for machine learning model. Also, rotation curve is path dependent, so it depends if you have drying or wetting. In this case, you could also here go for capillary pressure, porosity as an input, and then we have here the output as a degree of saturation. And we have here the different hidden layers with different number of neurons. So, and then if we train our model, then we see that it can predict different passes. So even if you have the same like capillary pressure, the degree of saturation would be different if you are on the drying path, or if you are on a wetting path. So this is a path-dependent process. It's very clearly important here. You could also generate another machine learning model to predict the velocity based on the pressure gradient or other macroscopic information, like again the porosity or the what you call the fabric tensor. It describes how the grains are connected to each other. And once you have the pressure gradient and velocity, then you could apply what we call the kind of inverse problem. So in which we have the velocity and the pressure gradient, and then we compute the permeability or the different entities of the permeability tensor. This is also a very important issue in porous media mechanics. And so in this case, so I mentioned at the beginning that we would like to figure out the settings of our neural network based on reinforcement learning. So we apply what we call self-played game for neural network meta-parameter selection. So the idea is applied actually in games, and the codes are also open access, so you can download them and you use them for the aim of your model. So the optimal neural network settings, mainly what kind of methodology you are applying. You could, for instance, for recurrent neural network, you can LSTM or GRU, number of hidden layers, number of neurons, dropout rates, optimizer, activation functions. The selection, it depends on the objectivity. And our objectivity here is to have an accurate model. So this is the objective of our work here. And we formulate this in some kind of graph, and the aim here is to find these selections that give us this accurate model. In this figure here, we have 2,592 possible combinations. So we have a lot of possible combinations. That's why it's really difficult to know what kind of optimal selection which we have by hand. So we can try only limited number of selections, and we would like to reach the optimal selection after a few steps. This is our aim. So the choice of the parameters is, as I said, can be formulated as a sequence of decisions to form directed graph, as you see here, with edges and vertices. So these are the edges and the vertices which are now going in this directed graph. And the selection is subjected to certain rules. For instance, we cannot select more than one type of neurons in each time. So we could not have at the same time GRU and LSTM, or we could not have at the same time 3 hidden layers and 2 hidden layers. So each selection should be specified in following certain rules. And as I said, the aim is to maximize the score, and the score will be, in this case, the accuracy of the model which we built based on this selection. It's something very similar to playing chess. Actually, this algorithm, as I said, coming from the game industry, and then it is also applied for playing of chess. Maybe some of you heard of the algorithms which are developed by a company. It's called DeepMind, and the game of Alpha and AlphaGo. So especially if we have Chinese in this course, they would know exactly how this game works. So game Go, it's very famous in Asia. First, we define the game. So the aim here is make a sequence of decisions to maximize the probability to win. This is what we do in chess. And then we have the game board, which is 8 by 8. In our case here, we have to make a sequence of decisions. So we have to select neural networks to maximize the score or accuracy of the resulting machine learning constitutive model. And the board in our case is a predefined settings, but we don't have selections yet. The game rule here in chess, we have for each piece we have specific rules. So for instance, for the bowing, we could have 1 or 2 moves. The knight has also different rules. The rook and the queen, the king, whatever. In our neural network selection game, we can choose only one of these settings at each step. And this is the rule which we have to follow. The game state in chess would have the places where we have the or the position of pieces. In our game of neural network selection, it will be the state, would be the different selections which we have already done. And then we have the game reward. In chess would be a win, a draw, or lose, which discontinuous. So we'd have this case, and the evaluation would be only available at the end of the game. So we'd have to finish the game and then we know if we have win or we have lost the game. In the game of neural network selection, we have to make a complete selection of the settings. And then we take these settings to train our model. And then after training the model, we can see if our model can give good accuracy or bad accuracy. So this is also available at the end of finishing the selection. And this is also an important difference. We use, as I said, deep reinforcement learning algorithm to figure out the correct selection, and which is based on this reward hypothesis. In the artificial intelligence agent and Markov decision process, we use what we call exploration and exploitation to discover the best actions that maximize the reward via interaction with the environment. So like very roughly, I don't want to go into details here because we don't have much time for this. We have the artificial neural network agent. So this is the algorithm that we have developed, deep reinforcement learning, which use the policy and value functions. And this is interacting with the environment, which includes our database, includes the validation process and the constraints which we have, for instance, the kinematics, the balance equations, and so on. And then it's an iterative process. In this case, the artificial intelligence agent interact with the environment in sequence steps. And this artificial neural network or artificial intelligence agent represents mapping from a certain state, or which will have selections and rewards, to probabilities of selecting new actions. And then you have the very important is the value functions, which allows us to predict the future rewards, because we would have the rewards after each selection, but the total rewards will be at the end of the whole selection. So we have like intermediate rewards, and then we apply what's called the Bellman equation to for the reward evaluation. We use the Monte Carlo tree search, which is a very effective search algorithm in the deep reinforcement learning. You can find details of this in this paper, Brown et al. And then we have the score, which is the prediction accuracy. So this algorithm, again, is not developed by us. It's developed from the game industry, from really important research groups, which work with very famous companies like with Google. And then they put their codes online, free, and everyone can use them for certain research work. So we use this for our research work, mainly during my work on this topic with the group in Columbia University. This is, for instance, how we evaluate our score. So we have to specify this score function, which is depending on the accuracy in connection with the training, validation, and test database. We give different weights for the different database. If we take, for instance, this table, it includes the all possible selections. In this table, we have 48,000 possible combinations. So it's a huge number of possible combination. That's why we should have an effective search algorithm, which we make use of only few number of these selections. In this case, I redefine the number of selections by 420 cases, which is less than 0.9%, and then I will get really a good selection after a few trials. You see here in this graph, this is the game score, and this is the deep reinforcement learning iteration. You see after 2 or 3 iterations, I'm getting a score which is almost 1. So 1 would be the exact selection. In this case, each iteration includes also episodes. So we have in each iteration 10 cases, so 10 selections which we compare with, and then we choose which one is more accurate, and then we have new selections afterwards. But we get very fast to the exact solution. And this is like an illustration of this tree search, or the decision tree, which we have like different selections. And then you see here the type of algorithm. This GRU is the algorithm which has been chosen by our reinforcement learning algorithm. 3 hidden layers, and then maybe we have here 8 neurons, dropout rates, and so on. So I think this the number of neurons was the 128. Yeah, but this is how the decision tree look like. If we look at the performance of the trained model, we see that if the score is like -1, it means we have a very bad score. So the blue lines, it shows the performance of our trained model. It's a very bad performance in comparison with the red line, which is the testing the database, which is unseen data. But when the scores start to improve, they have here -0.28. Then I have here 0.3, which is getting better, and then we have here a score of 0.9. This is a very nicely trained model, and it gives you a very good accuracy. So this is showing that the algorithm can figure out this is a good solution very fastly or very quickly. And then if we implement the trained model within the finite element framework, then we can also see how the big boundary value problem look like. So we include this in this boundary value problem. It's unsaturated porous media. We apply on the left-hand boundary condition drying and wetting curve here through changing the pressure of the liquid. And we are looking mainly at the pressure and degree of saturation at this point in the domain, and point E. And we look also at the stability of the model, because this is a very important issue which we have to address. We see that for the machine learning model, which is a blue curve here, it's distinguishing between the drying process and the wetting processes. However, the red line, which is a phenomenological model, it does not distinguish between these two curves, which give us a lot of errors here in the middle. So it shows that the machine learning model is very much better. We have stability issues with regard to machine learning, which we are now working on, because we would have a kind of explicit time step. So we have to figure out like optimal time step in order to get stable solution. This is again showing some differences between a phenomenological model and a machine learning model. It's showing that the flow direction would be, for instance, sorry, this is a functional model, this is a phenomenological model, and this is the machine learning model. They are showing the same flow direction at some certain time step. However, at another time step, it shows exactly the opposite flow direction, which should give us an idea how important to have accurate material model, because this might be exactly the opposite behavior, and this is very dangerous, and it reduces the trust and the reliability of our machine of our material model. Okay. We are working on different future aspects here, extending the machine learning model to overcome stability issues, which I mentioned in the last slide. We are now working on extending this model to capture the flow in fractured porous media and replace different phenomenological models by data-driven models. We also would like to go for machine learning based strategies to identify the material parameters of our material model. So this is another approach. We could use this deep reinforcement learning algorithm in the design of engineering systems. This is also one of the future topics. And this is the work on this topic has been done over like several years now. It was supported also from different institutions. Especially, I did most of my work on this in Columbia University with Professor Wai-Ching Sun and some colleagues there. And also a part of it was here at the RWTH Aachen with Professor Bernd Market, where the support is also appreciated. And if you are interested in more details, we have also a number of publications, like 3 papers. You can also access this freely. And yeah, with this, I'm at the end of this presentation. Thank you for your attention, and sorry for being a little bit too lengthy. But there are a lot of details, and feel free now to ask any question. Thank you.
I have a question. I'm not too familiar with the network in general. So from intuition, I would say the more neurons you have, the better, the more accurate the network is. Is that true? Or sometimes is it better to have less neurons?
You mean
layers, for instance?
The number of neurons, you mean?
Right. That's it.
Your voice is a little bit not clear. You mean here, if you go here, the number of neurons or the number of hidden layers, you mean?
Both, actually. I mean, is it better to have the most possible layers and neurons, or?
It's not, no. Not necessarily. There is an optimal number of hidden layers and optimal number of neurons, which give you best model. Let's say, I mean, most people do it like try and error. So try to increase, decrease, and see if it's effective. Some models, they are not really so sensitive to the number of neurons. But in general, if you increase the number of hidden layers, the number of neurons in each hidden layer, you are increasing the cost of the training. So it's already more expensive. But it doesn't necessarily mean that you are also increasing the accuracy. No, it's not necessarily. There's a specific number of hidden layers. So most people take 2 or 3 hidden layers and maybe 60, 70 neurons. It give you, in my case, it was like this, but you have to figure out the optimal number. Yeah. And that's why we go for this reinforcement learning, which is only a tool to helps us to that helps us to figure out this optimal number. Yeah.
Okay, thank you. And I had another question from slide 5, which was about data-driven approximation and optimization of the parameters. So,
number 5, you mean here?
Yes, that one.
What was the question?
So I guess the advantage of So I guess the advantage of the first phenomenological problem models is that it's continuous by nature, because you define the function to be continuous. So it's from a physical point of view, it's coherent with the fact that it's actual material. But if you use data-driven computing, can there be some jumps between the solutions that you find because the points are scattered? I mean, is it compatible with the fact that materials behaviors are continuous?
Yeah, this is a very important point actually, and this was a matter of discussion in the community, especially the non-believers in these approaches like data-driven or machine learning approach. They always criticize this issue, especially if you go one slide back. You see here we have divergence of sigma, and sigma includes gradient of the strain, or a gradient of this displacement. So, or here we have divergence gradient. So you have always to find the derivation, and then if you have continuous function, then you can take the derivation and then take the gradient, let's say. And this is also a very important issue. Yeah, there are some techniques to overcome this. So as you see here, I'm training the strain and the stress. I'm already training the gradient. It's already there. So this is one way to overcome this challenge. Yeah, and it's phenomenological behavior here. It's the function itself. It's a phenomenological function. So it includes also inaccuracy. In this way, because if, there are no way to get exactly or to capture the whole data point, and there are some other factors which is also coming from nature. These continuous functions assume always that this material will behave like this, but because we have at the microscopic scale we have heterogeneity, so in real materials you could have different properties which cannot be considered in the model. So this continuous function will not consider this heterogeneity in an accurate way. And that's why the data points might be more close to the reality. But as I said, if your material model, which is very much accurate, this might give you maybe better performance, it depends. But more accuracy, it means maybe you have 20, 30 material parameters, which is not possible to get. So as an engineer, you have to decide and you have to see the computational capacity, and then you take a decision about which approach you go for. But what I want to mention here, these approaches, this data-driven and machine learning, they are getting more and more attention. And that's why if you go for either research in the future, PhD, something like this, or you go for companies, then many of them are looking for people who are familiar with these approaches. Many people see there are big potential with these approaches, so they are still in the development phase, but they might be the topics of the future. Yeah.
Okay, thank you. And one last question, if no one wants to ask. So do you consider that all the data points are perfectly accurate, or can you take into account some inaccuracy in the data points? Like, do you consider that all the measurements and low-scale computations are perfect, or can you take into account the fact that maybe these points are not exactly perfectly fitting to reality?
Yeah, okay. If I understand your question correctly, so it depends on the way you generate your database. So if you are generating the database from some surrogate models from lower scale simulations, like I did before, I take a crystal and I apply the crystal. So this is an algorithm. So you can take all the data points in this case. So they are reliable because the model which you have at the lower scale, it will be consistent every time you make it run. But if your data point is coming from laboratory, then you have to apply the same rules for judging the quality of the data. So if you repeat the test 5 times and one of these tests is giving unrealistic values, so you have to exclude this because there are something in the testing machine or in the sensors which you are using to like to measure the data. So you have to make judgment about the quality of the database. But this is a step which come before the machine learning. So, and this is applied not only for machine learning or data-based approaches, but also applied for different for if you are deriving phonological material model. So first you have to choose the database, so which should be reliable. Excludes the data which is far from reality, which are showing that they have a problem with the data, and then you take this for the generating of the machine of the model. And this is, as I said, for both for phenomenological or for data driven. I don't know if I answered your question.
Yes, it's great. Thank you very much.
Okay. You're welcome. So there are some questions in the chat. So Kamlai is asking, in the composite material, do we need to consider the porosity part to the behavior of the material? So in composite material, we don't have porosity. I think you mean volume fraction of each of the yeah, here. I mean. As I said, in the machine learning model or the data-driven approach, you can include whatever microscopic information you have. So you can include really a lot of information which maybe initially you don't think that they are important. And you can include them then in the machine learning model, and then maybe you discover new dependencies. So in many phenomenological models, they don't consider maybe the, let's say, the volume fraction or the how much like inclusion we have with respect to the total volume of the RVE or other material properties which are maybe it seems at the very big at the beginning maybe they are not relevant, so they could be included in the machine learning model, and yeah, they might have effects, they might not, but your machine learning model can figure this out. So this is a very important issue in data-driven approaches. So let's say the question is not you can consider the porosity or the volume fraction, and if you have this information available, then you can include it without any problem, and then maybe it affects. We have another question from Hazal. How do we avoid the fall into the local minimum instead of global one? I think you are referring to, let me go to that slide. Yeah, is this one? It's difficult to avoid. So you can, in the training, if you see that your the loss function, this one is getting to 0, it's getting very much getting to 10 minus 7, 10 minus 8, it means that you have already a very good accuracy. So you cannot you can assume that you have already local minimum. But if you are keeping training and this loss function is not getting too small, to maybe 10 to power minus 2, and then getting then a kind of straight line, then it's that you are not getting global minimum. It's difficult.